Have you ever wondered why Java has so many collections? ArrayList, LinkedList, HashSet, TreeSet, HashMap, ConcurrentHashMap. If they all store data, why do we need so many? And more importantly, which one should you actually use in a real project? This is one of the most common areas where beginners get confused and where interviews love asking questions. In this video, we'll understand the complete Java collections framework from scratch using simple examples. By the end of this video, you'll know what each collection is, when to use it, and how to choose the right one for your requirements. So let's get started. Before collections existed, Java developers mainly used arrays to store multiple values. Arrays work well for fixed-size data. But imagine you're building an employee management system. Initially, you create an array of size 100. Tomorrow your company hires 101 employees. What now? The array can't grow automatically. You'll have to create a new larger array and manually copy all the existing elements. That's not only inconvenient but also inefficient. Arrays also make insertion and deletion difficult. If you insert an element in the middle, every element after it has to shift. Similarly, deleting an element also requires shifting. Searching is another challenge because arrays only store data, they don't provide convenient APIs for finding or organizing it. Developers needed something more flexible. Let's understand the biggest limitation first. Arrays have a fixed size. Once you create an array of size 5, it will always remain size 5. Even if it contains only one element, the remaining memory is reserved. And if you need more than 5 elements, you cannot simply extend the same array. You have to create a new array with a larger capacity and copy everything. Imagine doing this repeatedly in a real-world application handling thousands of records. Clearly, this isn't practical. Now suppose you have an array of student names. You want to insert a new student at index 2. Every element after index 2 has to shift one position to the right. Similarly, if you delete an element, all remaining elements shift to fill the gap. These operations become expensive as the array grows. This is one of the reasons why different collection implementations exist. Some collections optimize reading. Others optimize insertion and deletion. We'll see those differences shortly. Collections solve almost all the problems we just discussed. They can grow dynamically. They provide ready-made methods like add, remove, contains, clear, size, and many more. You no longer have to manually resize arrays or write repetitive utility code. More importantly, Java doesn't provide just one collection. It provides specialized collections for different requirements. Need ordering? There's one collection. Need uniqueness? There's another. Need sorting? There's another. Need thread safety? Again, there's a different implementation. Understanding which collection to choose is the real goal of this video. This diagram gives you the complete picture of the Java collections framework. At the very top, we have the iterable interface. Anything that implements the iterable interface can be traversed using the enhanced for each loop. Below that comes the collection interface. Think of collection as the common parent interface for most collection types in Java. From collection, we have 3 major branches: list, set, and queue. Each branch is designed to solve a different problem. List stores ordered elements and allows duplicates. Set stores unique elements. Queue processes elements in sequence. Later in this video, we'll explore each one individually. Separately, you'll notice map. This is a very important interview concept. Although map is part of the Java collections framework, it does not extend the collection interface. Instead, map has its own separate interface hierarchy because it stores key-value pairs, whereas collection is designed to work with individual elements. We'll understand this difference in the next section. Think of the collection interface as a common contract. It defines operations supported by most collection types. Methods like add, remove, contains, size, clear, and is empty are defined here. List, set, and queue are all interfaces that extend the collection interface. Later, concrete classes like ArrayList, LinkedList, HashSet, and PriorityQueue implement those interfaces. That's why they all share common operations while still behaving differently. Many beginners ask this question. If map is part of the collections framework, why doesn't it extend collection? The reason is simple. The collection interface represents a group of individual elements. A map stores key-value pairs. For example, employee ID employee object, product ID product details, roll number student. Since the data model and operations are fundamentally different, map has its own interface hierarchy. That's why you'll often hear this interview question. Map is part of the Java collections framework, but it does not extend the collection interface. Let's start with the most commonly used collection, list. A list stores elements in insertion order. That means if you add A, then B, then C, you'll always retrieve them in the same order. Lists also allow duplicate values. If the value Java appears 5 times, all 5 are stored. Another important feature is indexing. Every element has a position starting from 0. So accessing an element by index is straightforward. Think about real-world examples like a playlist, a to-do list, shopping cart items, or exam questions. In all these cases, order matters and duplicates may be allowed. Java provides 3 common list implementations: ArrayList, LinkedList, and Vector. Let's quickly understand when to use each one. ArrayList is the most commonly used list implementation in Java. If you're unsure which list to choose, ArrayList is usually the best starting point. It maintains insertion order. It allows duplicate elements. And because it stores elements in a dynamic array internally, accessing an element by index is extremely fast. That's why ArrayList is ideal when your application performs many read operations. Examples include displaying products, loading employee records, showing customer lists, or reading configuration data. However, there's one trade-off. If you frequently insert or delete elements in the middle of the list, ArrayList becomes less efficient because the remaining elements need to shift. So remember this simple rule. Use ArrayList when reading data is much more common than modifying it. This is why you'll see ArrayList used in a large percentage of real-world Java applications. Don't worry about how it resizes internally or how it grows in capacity. That deserves a dedicated video, and we'll cover all of that later in this playlist. Now that you understand why ArrayList is so popular, let's look at another implementation that takes a completely different approach: LinkedList. You'll see why developers choose it when insertions and deletions become the priority. We just learned that ArrayList is great for fast access. But what if your application frequently inserts or removes elements? That's where LinkedList comes in. Unlike ArrayList, LinkedList stores elements as connected nodes rather than a continuous array. Because of this, adding or removing elements, especially at the beginning or end, is much more efficient. Imagine a train where each coach is connected to the next one. If you want to add another coach, you simply connect it. You don't have to move the entire train. That's the basic idea behind LinkedList. However, there is a trade-off. Since elements are connected through links, Java has to traverse the list to reach a particular index. So random access is slower compared to ArrayList. A simple rule to remember is: if your application mostly reads data, choose ArrayList. If your application frequently inserts or deletes data, LinkedList is often the better choice. Examples include browser history, undo and redo operations, playlists, and queue-like processing. We'll explore its internal working in detail in a dedicated LinkedList video later. Now let's talk about Vector. At first glance, Vector looks very similar to ArrayList. It also maintains insertion order. It also allows duplicate elements. But there's one important difference. Vector is synchronized. That means its methods are thread-safe, making it suitable for multi-threaded environments. The downside is that synchronization adds overhead, making Vector slower than ArrayList in most single-threaded applications. That's why modern Java development rarely uses Vector for new projects. Instead, developers generally prefer ArrayList. You may still encounter Vector in older enterprise applications, so it's worth knowing for interviews. A simple memory trick: Vector equals legacy plus synchronized. So these are the 3 major list implementations. Now let's move to another category where duplicate values are no longer allowed. A set is designed for one primary purpose: uniqueness. Unlike a list, a set automatically removes duplicate elements. If you try to add the same value multiple times, only one copy is stored. Think about storing unique email addresses, unique usernames, unique employee IDs, or unique product categories. Duplicates simply don't make sense in these scenarios. Another important point is that most set implementations don't provide index-based access. You care about whether an element exists, not where it exists. Java provides 3 commonly used set implementations: HashSet, LinkedHashSet, and TreeSet. Each solves a slightly different problem. HashSet is the most commonly used implementation of set. It stores only unique elements. If you attempt to add a duplicate value, HashSet simply ignores it. One important characteristic is that HashSet does not maintain insertion order. If you insert A, B, and C, they may be returned in a completely different order. That's perfectly normal. The advantage is performance. HashSet provides very fast add, remove, and search operations. That's why it's commonly used for removing duplicates, checking whether an element already exists, managing permissions, and storing unique identifiers. Here's a simple rule: need uniqueness with maximum performance? Choose HashSet. Now suppose uniqueness is still important, but you also want to preserve the order in which elements were inserted. That's exactly what LinkedHashSet provides. It combines the uniqueness of HashSet with insertion order preservation. So if you insert Java, Spring, Docker, Kubernetes, they'll always be returned in that same order. This makes LinkedHashSet useful for displaying unique records while preserving user input order. Examples include recently searched items, unique browsing history, ordered tags, and configuration entries. A simple memory trick. LinkedHashSet equals HashSet plus order. Finally, we have TreeSet. TreeSet also stores only unique elements. But instead of maintaining insertion order, it automatically keeps elements sorted. By default, sorting happens in natural order. For numbers, that's ascending order. For strings, it's alphabetical order. Or you can provide your own comparator for custom sorting. Since TreeSet keeps everything sorted, it performs a little more work internally. As a result, it's generally slower than HashSet. But in return, you get ordered data automatically. TreeSet is ideal for leaderboards, rankings, sorted reports, autocomplete suggestions, and range-based searches. So remember, HashSet for uniqueness, LinkedHashSet for uniqueness with insertion order, TreeSet for uniqueness with sorted order. We've now covered lists and sets. Let's move to another very important collection category, queues. A queue follows the FIFO principle. First in, first out. Imagine standing in a ticket counter line. The first person to join the line is the first one to be served. That's exactly how a queue behaves. New elements are added at the rear. Existing elements are removed from the front. Queues are extremely useful whenever processing order matters. Real-world examples include print queues, CPU scheduling, message processing, customer support systems, and task scheduling. Java provides multiple queue implementations, but the two you'll use most often are PriorityQueue and ArrayDeque. PriorityQueue is different from a normal queue. Instead of processing elements in the order they arrive, it processes them based on priority. By default, the smallest element has the highest priority. So even if 50 was inserted first, and 10 was inserted later, removing an element will return 10 first. That's because PriorityQueue automatically arranges elements according to priority. Think about a hospital emergency room. Patients aren't always treated based on arrival time. More critical patients are treated first. That's exactly how PriorityQueue works. Common applications include CPU scheduling, Dijkstra's shortest path algorithm, task scheduling, event processing, and finding the top k largest or smallest elements. A simple memory trick. Priority beats arrival order. The second popular queue implementation is ArrayDeque. The word deque stands for double-ended queue. Unlike a normal queue, ArrayDeque allows insertion and removal from both ends. That means you can add elements at the front, add elements at the back, remove from the front, or remove from the back. Because of this flexibility, ArrayDeque can behave as both a queue using FIFO and a stack using LIFO. It also offers excellent performance and is generally preferred over LinkedList for queue and stack operations. Real-world examples include browser navigation, undo-redo functionality, sliding window algorithms, palindrome checking, and graph traversal. A simple rule: if you need fast operations at both ends, ArrayDeque is usually the best choice. So far we've covered lists, sets, and queues. But one of the most important collections in real-world Java applications is still left, the map interface. In the next section, we'll explore HashMap, LinkedHashMap, TreeMap, ConcurrentHashMap, learn how to choose the right collection for any requirement, and finish with interview tips that can help you confidently answer Java collections questions. So far, we've looked at collections that store individual elements. But in real-world applications, we often need to store data as key-value pairs. That's exactly what a map is designed for. Think about a student management system. Every student has a unique roll number. Using that roll number, you can quickly retrieve the student's information. Here, the roll number is the key, and the student object is the value. Another example is a user profile. User ID maps to user details. Product ID maps to product information. Country code maps to country name. In a map, keys must be unique, but values can be duplicated. And remember the interview point we discussed earlier. Map is part of the Java collections framework, but it does not implement the collection interface because it stores key-value pairs instead of individual objects. Java provides several map implementations, each designed for different requirements. The most commonly used implementation of map is HashMap. If you ask experienced Java developers which map they use the most, the answer is usually HashMap. HashMap stores data as key-value pairs. It allows one null key and multiple null values. One important characteristic is that it does not maintain insertion order. If you insert entries in a particular order, you shouldn't expect to retrieve them in the same order. The biggest advantage of HashMap is its performance. Searching, inserting, and removing elements are extremely fast in most situations. That's why HashMap is widely used in caching, session management, configuration storage, counting frequencies, and lookup tables. Here's an interview tip. If you put a value using an existing key, HashMap doesn't create a new entry, it simply updates the existing value. A simple memory trick. HashMap equals fast lookup, no ordering. We'll dedicate an entire video to understanding HashMap internals, hashing, buckets, collisions, resizing, and treeification. Sometimes, fast lookup alone isn't enough. What if you also want to preserve the order in which entries were inserted? That's where LinkedHashMap comes in. LinkedHashMap behaves much like HashMap, but it also maintains insertion order. So if you add entries in the order A, B, C, they'll be returned in the same order during iteration. This makes it useful for displaying ordered data, generating reports, reading configuration files, and maintaining predictable output. Another interesting feature is that LinkedHashMap can also maintain access order, making it useful for implementing simple LRU, least recently used, caches. So remember, LinkedHashMap equals HashMap plus insertion order. Now suppose your requirement is different. Instead of insertion order, you want the keys to remain sorted automatically. That's exactly what TreeMap provides. TreeMap stores key-value pairs in sorted order based on the key. By default, sorting follows the natural order, but you can also provide your own comparator for custom sorting. Since TreeMap keeps data sorted internally, operations are generally slower than HashMap. But in return, you gain automatic ordering and powerful navigation methods such as finding the next higher key, lower key, or retrieving a range of entries. TreeMap is commonly used for leaderboards, reporting, scheduling systems, dictionaries, and any application where sorted data is important. A simple memory trick. TreeMap equals sorted keys. Finally, let's talk about ConcurrentHashMap. In multi-threaded applications, multiple threads may try to read and update a map at the same time. A regular HashMap isn't designed for this scenario and can lead to inconsistent behavior. ConcurrentHashMap solves this problem. It is specifically designed for high concurrency environments. Multiple threads can safely read and update the map without locking the entire structure. This provides much better performance than older synchronized alternatives like Hashtable. You'll commonly find ConcurrentHashMap in web applications, microservices, caching systems, real-time analytics, and applications processing many requests simultaneously. Here's an interview tip. Don't use ConcurrentHashMap just because it's thread safe. Use it only when multiple threads actually access the same map. Otherwise, HashMap is usually the better choice because it has less synchronization overhead. A simple rule. HashMap for single-threaded scenarios. ConcurrentHashMap for concurrent access. We've now explored the most commonly used collections. But when you're building an application, the real question is, which one should you choose? Let's simplify everything we've learned into one practical decision table. If you need fast key-based lookup, choose HashMap. If your keys need to stay sorted, use TreeMap. If you need unique elements, use HashSet. If you need an ordered collection that allows duplicates, ArrayList is usually the best choice. If processing order is important, choose a queue. If priority matters more than arrival order, use PriorityQueue. And if your application is accessed by multiple threads, consider ConcurrentHashMap. Instead of memorizing every collection, first identify your requirement. Do I need ordering? Do I need uniqueness? Do I need sorting? Do I need thread safety? Once you answer those questions, selecting the right collection becomes much easier. One question that often comes up is, which collection is the fastest? The answer is, it depends. No collection is best for every situation. ArrayList is excellent for fast random access. LinkedList performs well when frequent insertions and deletions are involved. HashMap and HashSet are generally very fast for searching and lookups. TreeMap and TreeSet trade some performance for automatic sorting. ConcurrentHashMap provides safe concurrent access with excellent scalability. So instead of asking, which collection is the fastest? Ask, which collection is best for my specific requirement? That's how experienced developers think. Before we wrap up, let's quickly go through some popular interview questions. What's the difference between collection and collections? Remember, collection is an interface. Collections is a utility class containing helpful static methods. Another favorite question. Why doesn't map implement collection? Because map stores key-value pairs, whereas collection stores individual objects. Which collections are thread-safe? Vector and Hashtable are synchronized legacy classes. For modern concurrent applications, prefer ConcurrentHashMap. Which collections maintain insertion order? ArrayList, LinkedList, LinkedHashSet, And LinkedHashMap. Which collections keep data sorted? TreeSet and TreeMap. And finally, don't just memorize definitions. Interviews often ask, why would you choose HashMap over TreeMap? Why would you use LinkedList instead of ArrayList? Your answer should always start with the requirement and then explain why that collection fits best. That's what demonstrates real understanding. Let's quickly recap everything we've covered. We started by understanding why arrays weren't enough and why the Java Collections framework was introduced. Then we explored the overall hierarchy of the framework. After that, we looked at lists for ordered data, sets for unique elements, queues for sequential processing, and maps for key-value storage. Finally, we learned how to choose the right collection based on real-world requirements instead of simply memorizing names. If you can explain what a collection does, when to use it, and why you chose it, you're already ahead of many developers in interviews. This video was designed to give you the complete picture of the Java Collections framework. In the upcoming videos, we'll take each collection one by one and explore it in much greater depth. We'll cover ArrayList, LinkedList, HashMap, HashSet, ConcurrentHashMap, TreeMap, comparable vs comparator, internal implementations, time complexities, common interview questions, and performance comparisons with practical coding examples. So if you're preparing for Java interviews or want to become a stronger backend developer, this playlist is made for you. If you found this video helpful, don't forget to like, share, and subscribe to Spring Java Lab so you don't miss the upcoming videos. Thanks for watching, and I'll see you in the next one.